Good evening, Josh. Kindly solve these problems in geometry about translations and rotations. Given points O1, O2, O3, O4 in the plane arbitrary point A, that AB moves successively by half turns about O1, O2, O3, O4. You can start uh, writing your solution at point P. That AB moves successively by half turns about. You can start basically.
Yun ang mga explain mo.
Okay, by half turns about O3, O4, O1, O2 to a point Q, show that P is equal to Q.
First, before even attempting this problem, we need to understand what the basis of the solution will be. So there is a suspicious regularity in this problem. Where is it? Here. O1, O2, O1, O2. There's also another suspicious grouping. O3, O4, O2, O4. Why? So it means there must be a reason to why that is occurring. So what happens when what happens when a point is moved by O1 and then O2, and then it stops, and then moved by O3 and then O4? So is that how can we prove that that is the same as moving it by O3 and O4, stopping, moving O1 and O2? That seems like it is similar to the commutative property of addition. A plus B, do this and then do that. Is it equal to doing this other operation the reverse way? B plus A. So that's the question. So this is a triangle, and then this is a specific point of rotation. This is the third triangle, and then there's another point of rotation, and this is the second degree turn triangle. From inspection, it appears that it is perfectly parallel to the first triangle, which is true because this is parallel to this one, because it's the half turn always preserves parallels, and then once again the preserving of the parallels will move this side to this side. So eventually doing that for all sides means that the entire triangle has the exact same length, because nothing changes when it is turned. It's only in the entire triangle does not deform. So the sides are the same, plus they are oriented in the exact same way because all of the sides are parallel. So this means the triangle has gone under a more simpler transformation, which is simply translation. So it means a half turn about two distinct points, or actually even the same point, will lead to a translation. The trivial part is when the triangle is rotated about the same point. Obviously, it's obviously the same. So the transformation is nothing. So this means, to a given extent, we can already know what this means. O1, half turn about O1, O2 means a translation, some sort of translation, and then plus another some sort of translation because of O3 and O4. So how can we prove that the translation from O3 to O4 and then the translation from O1 to O2 is exactly the same as this translation? Translation, as you can see here, is something familiar, which is a vector, magnitude and direction. So here, if we say that uh, if the rotation half turn about O1 and then O2 successively is vector x here, and then from O3 to O4, O3, and then O4, this is vector y. So for this figure where it went O1, O2, and then O3, and then O4, this is P. And then for this one where it went O3, O4, O1, and then O2, it's Q. So by inspection, they're the same point, obviously, which is what we want to prove. So finally, this is a vector and it's another vector, and they happen to come from the same point, which is obvious because of course A is the point that's being moved anyway. So of course the vector should always start with A because A is being the one moved and it always starts from the same direction. So that is nice because it means the sum also emanates from A. So if this I will just put it here temporarily. If this is A moving here, this is X, uh the sum will be it's about the same. Where is it? So using eyeball mechanics, it's like here. So it's close to Q, which is actually true. Because if we move in this figure, I forgot to put the bigger picture sort of. This is a movement by O3 and then O4. So it has to go to P. This is a motion Q plus Y. This is, I know that's not Q. Why did I say Q? This is a motion vector X plus vector Y. So what seems to be strange here? Just by inspection, they seem to be perfectly parallel. Are they? Let's see. Uh, yes, they are.
Yes.
They're perfectly parallel. So it's so anyway, there's a sneaking through here behind this main image. So anyway, uh, here goes this is Y, vector Y. Then it's to rotate again. We need to put this a little lower. So there will be room for you to put the extremely long jumping distance. Here, something like so where would that be? It's like here. And then we're thinking about oh, oh wait, let me put something here from here. So O3, O4, here, and about 2. Here, oh, so eyeballing technique is rather accurate actually. Uh, I hope that can be understood anyway.
Label it.
Yes, wait. This is O1. This is the reflection of the what V1. So this is V1 prime. And then the next one is all the way across O2. Nice luck. So it's literally the very zone. So what's this example? So what other noticeable similarity seems to be occurring here? This line. Wait, I I will move this temporarily. This line, I hope my eyeball's good. Oh, it's good enough. So it's approximately parallel over there. It's almost just eyeball technique, but it's close enough. So it's almost parallel, which is supposed to be the case. It should be parallel. So it's also parallel. So then when we add these, wait. So this is original x plus y. So what this there's this resultant vector from A to P. This is x plus y. And then there's another one here. X, Y. So they also again by maybe my eyeballing technique is too good. Or maybe this is just plain luck. They look exactly the same.
Yeah.
They're actually perfectly parallel and they look like the same measure. So here this is why. Oh wait, why did I spoil the beans? Why did I spill the beans? It was not actually supposed to be written that way. It's the other way around. But anyway, that's it. It's as simple as that. Actually, vector the main point here is that vector addition is simply commutative. Earlier we proved that two half turns will result in a translation which can be said to be a vector. So this is one vector plus another vector and this other vector plus the same vector earlier. So vector addition is commutative. That is the one of the basis of one of the base concepts of vectors. That's what
Yeah,
different.
fundamental concept.
Yes, it also differentiates them from pseudo vectors. The fact that they are commutative. So that's an intrinsic property of vectors. So vector x plus vector y is equal to vector y plus vector x. So as simple as that, the rotations about O1 plus O2, which is a vector, plus the rotations about the other O3 and O4 is equivalent all in the other way, simply because they're commutative. So the translation in the end is exactly the same. So since that the translation is exactly the same, it will lead to the same point.
Therefore,
So that's little bit. Thanks for watching.
thanks for watching.